And as I mentioned, flip-flops with different control sets cannot be packed into the same slice. So in this example, we see 3 flip-flops resynthesized to force some control signals to associated LUT inputs, so that these registers can be packed into the same slice. This will get you better device utilization and better speed. There are 3 ways to get the FPGA resources you need into your design. You can either infer logic with your synthesis tool, instantiate primitives from the Xilinx Unified Library, or instantiate an optimized component from the core generator. One of the biggest challenges for new users is to make certain that they are inferring the appropriate resources. First of all, one of the best ways to check that you're getting the best resources is to use your synthesis tool schematic viewer. All of the high-end synthesis tools have schematic viewers. Viewers are used to graphically display a gate-level version of your netlist and also a technology view of your netlist. While a gate-level netlist is worthwhile to check the Boolean optimization produced by your synthesis tool, the technology viewer helps you understand what Xilinx primitives were inferred, or more importantly, what primitives were not inferred by your synthesis tool. A primitive is a resource that is written to the netlist that represents a particular FPGA resource, such as a LUT, shift register LUT, distributed RAM, etc. Xilinx provides a library of primitives called the Xilinx Unified Library to all of our synthesis partners, as well as to our customers, so they can create netlists that are optimal for their customers. While this same library is available to you anytime you want to instantiate a primitive into your FPGA. The core generator and the architecture wizard make larger optimized components available to you. While some cores have a charge associated with them, most do not have a charge associated with them. The cores range from simple components to large, high complex IP. The architecture wizard, frankly, is most commonly used for creation of custom PLL and DCM components. All primary slice resources can be inferred by XST and Simplify. This includes LUTs, flip-flops, shift register LUTs, muxes, and carry logic. However, you must be sure to code for the resources properly. This means that if you define a flip-flop with an incompatible combination of control signals, you'll get something slightly different, probably with the LUT input used for a control signal. Likewise, the shift register LUT is non-loadable, has no reset, and only supports a serial functionality. So if you code for a parallel read, you'll get a pure register implementation, and this again may not be what you expected. Similarly, muxes need to be coded with a case statement, and carry logic should use the proper arithmetic operator. Don't code for the XOR functionality if you're targeting the carry logic, otherwise you just won't get it. In general, Inference is best and preferred by our customers. It assures portability to another technology and is of course reusable. However, most customers will have to do some instantiation to get the most out of the FPGA. As I mentioned earlier, a list of Xilinx primitives and their behavior can be found from the Xilinx Unified Libraries Guide. This is available at support.xilinx.com or can be found from the Help menu in the ISE software. This will describe all the ports and attributes that can be customized. There is also a complete description of the XST attributes located from the software manual webpage. This is always a useful resource for inferring logic and learning good HDL coding styles. The core generator and architecture wizard help you instantiate a high-level component. These cores are optimized and make designing for all the detailed functionality of things like the DCM or PLL easier. They also provide access to some very powerful design tools that can create common sophisticated components at no charge. In summary, all slices contain 4 6-input LUTs and 8 registers. The LUTs can perform any combinatorial function of up to 6 inputs or be implemented as 2 functions of 5 inputs. 4 of the 8 registers can be used as flip-flops or latches. The remaining 4 can only be used as flip-flops. Flip-flops have active high clock enable inputs and active high synchronous or asynchronous set-reset inputs. There are a couple of different slices as well. Slice cell slices also contain carry logic and the dedicated muxes. The mux F7 multiplexers combine LUT outputs to create 7 input functions or 8 input multiplexers. The mux F8 multiplexers combine the mux F7 outputs to create 8 input functions or 16 input multiplexers. The carry logic can be used to implement fast addition, subtraction, and comparison operations. The LUTs in the slice M can also be used as shift registers or 64-bit distributed memories. And finally, manage your control set usage so you can reduce the size and increase the speed of your design. Well, there's a lot of useful information about inference and synthesis attributes in the Synthesis and Simulation Design Guide. This is available from the ISE software using its help menu or directly from support.xilinx.com. The XST User Guide provides very helpful coding recommendations that all Xilinx users should live by. It also includes a detailed description about all of XST's synthesis options. This information can also be found from the help menu. If you would like to see what other courses we offer or what other free RELs are available, go to the Xilinx education link you see here. I would also like to mention again that there are architecture modules available that discuss the basics of Xilinx's newest devices. You may find this useful, especially if you want to learn more about the device differences. Again, my name is Frank Nelson. You've been listening to the basic FPGA architecture module for the Spartan-6 device family. Thanks for listening, and thanks for your business.